A team of researchers working at Stanford University has extended the record for quantum superposition at the macroscopic level, from 1 to 54 centimeters. In their paper published in the journal Nature, the team describes the experiment they conducted, their results, and also discuss what their findings might mean for researchers looking to find the cut-off point between superposition as it applies to macroscopic objects versus those that only exist at the quantum level. Nature has also published an editorial on the work done by the team, describing their experiment and summarizing their results. Scientists entangling quantum particles and even whole atoms has been in the news a lot over the past couple of years as experiments have been conducted with the goal of attempting to better understand the strange phenomenon, and much has been learned. But, as scientists figure out how to entangle two particles at ever greater distances apart, there has come questions about the size of objects that can be entangled. Schrödinger's cat has come up in several such discussions as theorists and those in the applied field seek to figure out if it might be truly possible to cause a whole cat to actually be in two places at once. In this new work, the team at Stanford has perhaps muddied the water even more, as they have extended the record for supposition from a mere 1 centimeter to just over half a meter. They did it by creating a Bose-Einstein condensate cloud made up of 10,000 rubidium atoms, inside of a super-chilled chamber, all initially in the same state. Next, they used lasers to push the cloud up into the 10-meter-high chamber, which also caused the atoms to enter one or the other of a given state. As the cloud reached the top of the chamber, the researchers noted that the wave function was a half and half mixture of the given states and represented positions that were 54 centimeters apart. When the cloud was allowed to fall back to the bottom of the chamber, the researchers confirmed that atoms appeared to have fallen from two different heights, proving that the cloud was held in a superposition state. The quantum superposition principle allows massive particles to be delocalized over distant positions. Though quantum mechanics has proved adept at describing the microscopic world, quantum superposition runs counter to intuitive conceptions of reality and locality when extended to the macroscopic scale, as exemplified by the thought experiment of Schrödinger's cat. Matter wave interferometers, which split and recombine wave packets in order to observe interference, provide a way to probe the superposition principle on macroscopic scales and explore the transition to classical physics. In such experiments, large wave packet separation is impeded by the need for long interaction times and large momentum beam splitters, which cause susceptibility to dephasing and decoherence. Here we use light pulse atom interferometry to realize quantum interference with wave packets separated by up to 54 centimeters on a timescale of 1 second. These results push quantum superposition into a new macroscopic regime, demonstrating that quantum superposition remains possible at the distances and timescales of everyday life. The sub-nanokelvin temperatures of the atoms and a compensation of transverse optical forces enable a large separation while maintaining an interference contrast of 28%. In addition to testing the superposition principle in a new regime, large quantum superposition states are vital to exploring gravity with atom interferometers in greater detail. We anticipate that these states could be used to increase sensitivity in tests of the equivalence principle, measure the gravitational Aharonov-Bohm effect, and eventually detect gravitational waves and phase shifts associated with general relativity.